Recording now. Good. So let's start the course. Let me. Okay. So you see the page, correct?
Yes.
We can.
Okay. So let me just also. And you're right, seeing my handwriting there. Correct?
Yes.
That's great. So let's start this meeting actually. Good. So great. So okay. So we talked previous time about P versus EXP versus R means those that you can decide in solvable in finite time. Then we talk about NP and co-NP, X hard problem or X complete problems, and about PSPACE, about L NP space that is equal to PSPACE, and essentially non-deterministic versions of that. And this kind of polynomial time hierarchy that exponential time belongs is a subset of exponential subspace, and then it is a subset of double exponential time, and so on and so forth. Good. Now, let's go back to here. When we defined the problem here for the problem of so this one session I can write it down easy here. Great. Okay. So here we talk about let me change the so we talk about NP complete problem or X hard or X complete problem. So X hard, we mentioned that it means that it is as hard as every other problem in the class X. And we defined as a X complete problem is the problem which is both in X, means X easy means belongs to X, and X hard, it means that as hard as any other problem in the class X. So here, this definition that what's the meaning of as hard as every problem in X, we need to, that begs the definition. And that's the thing that we want to talk about it. So of course, belonging to X means that, as we have seen, belonging to NP or PSPACE or everything, that's easy because you need to say, for example, for NP, if I give a certificate whether which is often a solution, which is a valid solution or not. That's the thing that we needed to do it for NP. But the question that what's the meaning of NP complete? That's the thing that makes it harder. Good. So here we are talking about this part. What does it mean as hard as this other problem? So this is the concept of reduction that I mentioned briefly before. We say that there is a reduction from A to B. If there is a polynomial time algorithm that can convert an instance of A to an instance of B. So this is very important. So a reduction from A to B means a polynomial time algorithm to convert an instance of A to an instance of B, such that the solutions to A and solutions to B becomes equal. Then what's the meaning of that? It means that if we can solve B, then we can solve A as well. So what's the meaning of that? It means that if B belongs to polynomial time, then A should also belong to polynomial time. If B belongs to NP, then A should belong to NP as well. So in some sense, B would be is at least as hard as A. Or we can say A is a special case of B. When there is a reduction from A to B. So just good. So for example, we say that there is a reduction from satisfiability to OR problem. What's the meaning of that? It means that OR problem actually can OR problem can solve satisfiability problem. So each instance of A can be solved. In some sense, you can consider it as a procedure that it gets the input to A, turn the input from A, the input of A to an input of B. Then we run the procedure B on that, and then we are the solution that we get it from that. You may also again change it a little bit, and from that we get a solution from A. So whenever there is a reduction from A to B, it means that the problem A is easier than B. And it means that this, as mentioned here, if we can solve B, then we can solve A as well. So now what's the meaning of that? It means that this problem B should be harder than A, because whenever we can solve B, we can solve A as well. As I mentioned, B is at least as hard as A. Now, these things that we are considering now, if you consider this is the class NP, we consider a subset of them. This is the NP-complete. NP-complete is the class of problems for which. So in some sense, what do we need to know? If we know only one problem in the class NP, that is every other problem in NP, I mean, this problem is harder than that, in a sense that this problem can solve any other problem in NP. Now, if we find any other problem, and we say that this problem, so this would be the problem A in some sense. And if we find any other problem B, and we can say that B is at least as hard as A, it means that B also should be in the complete class of this. So that's the way that actually it works. So we have one problem. This actually this is the assumption part. This problem actually is a satisfiability problem, or other problems like tree partition and others that we know that they are belonging to the class NP-complete. It means that these are as hard as any other problems in NP. Now, to show that any other problem is NP-complete, we only need to show that this problem is as hard as any of these well-known problems that we know that they belong to NP-completes. The first problem that has been actually shown that this problem is as hard as the whole class NP was the satisfiability problem. I mean, that I will talk about it. This was a Cook, Stephen Cook's proof that actually he got a Turing Award for that. That is a non-trivial proof. How the idea is that how we can show that a Turing machine can be actually mentioned by satisfiability problem. Why? Because everything that we have in NP, we are talking about in the Turing machine. And Turing machine, I think you should know that, I mean, we have some kind of tape essentially, and then at any time, this is essentially the computer. You can think about it as a memory. You can go left and right at any time on this, and then you can change the value of this guy. And we have, say, polynomial space that you can do that. So this problem, this is essentially the Turing machine. And even there was this reduction was there. So there is a reduction from SAT to Turing machine. What's the meaning of that? It shows that any problem that you are SAT problem actually is harder than Turing machine. And anything that we can represent this way by a Turing machine, we can also represent it by a satisfiability problem. So this is the Cook's result. Stephen Cook, that's the main result that he had it, and he got the Turing Award for that. But after that, then we need to, for any other problem, to show that this problem, so this is the SAT problem belongs to the class NP and is as hard as NP. That's the reason that it becomes the NP complete. So SAT belongs to this complete class. Now, given that result, now any other problem you want to say that it is NP complete, in some sense, we need to say that that problem is as hard as satisfiability and belongs to NP, then it becomes an NP complete problem. Any question? Everything is clear? Please, I mean, unmute and answer. Great. Good. So here, so that's the concept of reduction essentially from this is a reduction from A to B. And that, as I mentioned, it means that B is at least as hard as A. So it means that so we say that there is a reduction, for example, from satisfiability to OR problem. It means that B is at least as hard as A, or A is a special case of B. Now, good. So we always, this, as I mentioned, for this class, I mean, the first name of the class was essentially assumptions. And reductions. So assumptions is that we know that this problem is NP hard, is NP complete, or other things that we know for, or different classes. We know that this problem, for example, complete for that class. The reduction part is exactly this one. So this reduction is very algorithmic. As I mentioned, to show this one, we need to consider the instance of when we have a reduction from A to B, we need to say that if you have any instance of A, we can change the input, give it to an oracle or a procedure that solves B. And then from the output, we can infer the output of A. So this can be a one call reduction. This is called CARP reduction. One call means that one time we are calling this procedure. Or it can be the multi-call reduction. This is the Turing reduction also there. So here we may actually, so this function, there is a function that solves the problem B. We may call it more than one time. it turns out, I mean, for lots of these classes that we are talking, especially about NP-complete, it doesn't matter. Is it one time or several times? Because if it is polynomial, then it is as long as sorry. As long as the number of times that we call it is polynomial, as long as the number of times that we are call it is polynomial, one call or multiple call, there is no difference. In particular constant, doesn't matter. So you can think about it. I mean, this, if the running time of this oracle is polynomial or exponential, that does not change if we are multiplying another polynomial there. If it is a polynomial, it still remains polynomial, and if it is exponential, it still remains exponential. Good. Some examples for algorithms that there are some kind of reduction. So, for example, for unweighted shortest path to weighted shortest path. So, what is the shortest path in the graph? I will just mention that such that you get familiar, because we are working with this problem. So this is a graph that we have, and then this is the shortest path from A to B. So you want to say that in this graph, what is the shortest path from A to B? So here there is a reduction from this is the problem A, this is the problem B. So we want to say that problem A can always be solved with a problem B. So in some sense, problem B we want to say is harder than problem A. Why? Because if we can solve, so it means that if we have a procedure for B, so we can always say that this is a procedure that solves. So we call it procedure B. It means that some problem that solve some function B, or like you can say this is. Maybe I will say it. This is the function B. So function B is the one that solves it. So can somebody say that why there is a reduction from A to B, where A is the unweighted shortest path and B is the weighted version? Please unmute and answer.
Well, you just weight every edge with like the same thing, and then solve the weighted version.
Yeah, exactly. So that is actually, you can show that if the, I mean, you can just put the weights equal to 1. And so in some sense, the weighted problem is harder than unweighted problem. You can say also the reverse. So this is also the reverse might be correct. So can we say that also the unweighted is as hard as weighted? Any ideas? Please unmute and answer.
So maybe you can come up with like more like you can add like more vertices to your graph, and like whatever the weight is, you add like as many vertices in between like each
yeah, so that's the thing. So
possible?
if this is if you consider these two guys from, I don't know, vertex A to vertex B, and the weight is 5, you may essentially add this temporary vertex T1, T2, and so on, T5, and this is B. And then you can add these guys. Actually, you need to put T4. 1 less than 5. Good. So you will just put these weights here, and then this we have it 5 essentially vertices, 5 things here. Good. That is so. This is. However, does this work? Does this work all the time, or there are some restrictions for that?
It will definitely work for constant weights, but I don't know beyond that.
So one case that is actually it has a problem. So as long as actually the weights are polynomial in the number of vertices, this works. So as long as weights are polynomial, weights are poly of n. Again, n is the main problem that we have. So the input, I mean, you may have several parameters. If there are several parameters, some of them we call it n. N is the main input. So here, for example, the number of vertices or the number of edges, you can consider both of them as n. And both of them are polynomial in each other. As long as the weights are polynomial of each other, then you know that the number of edges of the original graph is polynomial, so times polynomial would be polynomial, so that should be fine. The only problematic case is the case that the weights are exponential. So note that, say, with n bits, we can represent some number like 2 to the n. Good. And note that the input size is still polynomial in n, because for each edge, we are just giving some numbers that the number of bits of this number is n, the number of vertices, say. So here, the total size of the input is still polynomial. However, this reduction does not work, because if we want to put it, then for each of these vertices, we may need to put 2 to the n vertices, because the size of these weights are large. So the size, there is a blow up in the input instance. And that's essentially so to do so, I mean, we need to actually spend exponential time to go from this problem A to B, because these are exponential things. And that essentially breaks down. So as long as the weights are polynomial, this problem, weighted and unweighted, are equivalent. As I mentioned, weighted is as hard as weighted, of course. Weighted is as hard as unweighted. And if the weights are polynomial, also we can say that unweighted is as hard as weighted. Clear? Questions?
It's clear to me.
Yeah, great. Okay, so I just want to make sure that, I mean, everyone gets it, because that's the important one. Actually, you will see this kind of reduction a lot in algorithms. Then we consider this is for lots of weighted problems. So there it is the case. As long as the weights are polynomial, usually weighted and unweighted are equal. But it depends on different problem. But when they become weights exponential, often we don't have such a reduction. You need to do smarter things. Great. So let me. Other problem. So the other problem is the mean product path. So like the mean sum path. We want to say that the mean sum path is, so this is again, we want to say from A to B. And we want to say that the problem B is as hard as problem A. So so you want to find, again, this is the, for example, in the shortest path, you want to find a path between two guys that some of the lengths of these guys are, say, minimized. I say that all the numbers are, say, positive. The same question that you may ask, what about I want to find a path that it is the product of these guys, the product of the weights are minimized. We can show that this problem, the sum version, is actually as hard as the product version. Why? Because if the product version is given to us, we are just taking the a logarithm of the weights. And then we are solving the mean sum problem on that. And because the logarithm of a product is equal to sum of the logarithms, then we can solve the mean sum problem to solve the mean product problem. So in that sense, the mean product path is easier than mean sum product. So here it means that A is easier to B, is easier than B because A can be reduced to B. Good. Longest path. This is another thing that, I mean, if you want to find the longest path in a graph, then you can essentially use the shortest path for that. That is, I mean, how can we do that? We can just do some kind of negation essentially for that, and we can do longest path to shortest path, but this is assuming that there is a shortest path that can solve for negative weights. That we may not have it, but generally this is the case that works. Another problem is this one, the mean weight k-step path to mean weight path. That's also, it is, so what is the, so these are all from the shortest path problem. So for example, for what is the mean weight path, the same things that you want to find from so from A to B, you want to find the shortest path from A to B. Now the question is that, what about, so here from A to B, you want to say that the minimum k-step path, so what is the minimum weight k-step path? It means that the number of these guys should be at most k. So if we have this restriction k, then we become this problem, mean weight k-step path. If we don't have this restriction of k, then we become, so if we do, there is no k, then we will do this one. So this means that it is arbitrary. In some sense, the mean weight k-step version is, I mean, there are more restrictions here, and we need to make sure that there is like satisfy all of these constraints. How can we do that? This is actually another trick that you can do it generally. So the typical thing is that when you have this one, you may actually have the graph, this graph that you have it, you may repeat this one k times. So you have, if you have a graph G here that you want to solve the problem, here you want to, you want to say that the mean weight problem actually can solve the mean weight k-step problem. So how can we do that? In the graph that is given to you for the mean weight, so there is an input graph that is given to you. From this graph G, I will create a graph G prime. So here it is essentially G, and this, the whole thing is the graph G prime. As I mentioned, we are changing the input. And how many copies of G prime I will put it? I will put k copies of G here. And then I will ask, what is the shortest path from here to here? Good. And what are the edges? All the edges that I have it, so there is no edges here. So I don't put any edges here, no edges here. All the edges would be from here to here. So if you have a vertex, so if you, in the G graph, if you have X and Y edge here, how do I put the things here? I will put X here and Y here, and I will put an edge here. Or, I mean, I can also do the reverse. If I have Y here and X here, also I will put an edge. But I don't put any edge from X to Y here. So there is no edges like this anymore, or no edges like this. So this part, essentially, this would be empty. So there is no edges here, no edges. So I will just essentially, these are the same vertices, but no edges. All the edges would be between these guys. And then I will say, okay, just solve the shortest path. So the shortest path, the issue is that in some sense, to find the shortest path, the only way is to for K version is that you will go from here to here essentially. This would be the K step. This would be the, so regular mean weight version would be the K version here in the original graph G. So this is the type of reduction. From G, we will go to G prime by putting this type of graph. And any questions so far? Good. So let's go to this one. And this is an important one. This is, again, this assumption and reduction. Almost all hardness proofs are by reductions from known hard problems to your problem. So again, almost all hardness proofs are by reductions from known hard problems to your problem. Why? Because this problem, if we know that this problem is hard, when you are doing it to your problem, it shows that your problem is as hard as those known problems as well. So that is important, that you need to consider, for example, well-known problem like SAT, like tripartition, etc. here, and then your own problem here. And of course, if you put for your own problem, then this your problem would be as hard as this other problem. So next time you can use your problem to do more reductions here as well. Good. So two important problems that we want to talk about these things. One is for the hardest problem, we have this 3-sat problem. So 3-sat for NP-completeness. So this is the question: can you satisfy? By satisfy that, can we make true a formula like this? X1 or of X2 or of X3, and of, so generally 3-sat is something like this. So we have like, or satisfiability or generally is this one. So we have and of a set of ORs. So sometimes actually OR is represented by this and the AND is represented by this. So these are equivalent. So this is the satisfiability problem that we are considering. And now these are some important things. So for example, if you have X1, X2, X3, these Xi's, these are called variables. A literal, either it is a variable or a negation of a variable. So each of these OR that we have it here, this is OR of a variable or its negation. In general, we call them literals. Literals, either this is a variable or not of a variable. That is called literals that we have seen here. And finally, we have each of these OR guys, we call them a clause. So each clause has several literals, and we have and of clauses. Good. And each of these, so each of them are essentially and of the classes, and of the clauses, and each of them in the 3-sat problem, here each clause has 3 literals. So 3 literals per clause, that is called a 3-sat problem. And this is an instance of 3-sat. So if we don't have any restriction on the size of the clause, a clause can have, I mean, up to n, like n again, the input size. Whenever I talk is about n is the input size. If we can have up to this number of clauses, up to number of this, if there is no restriction, particular restriction on the size of the clauses, then this problem is called satisfiability. So that originally has been proved essentially that this problem is as hard as like the Turing machine satisfiability. But then the 3-SAT is introduced, and then we mainly, and we showed that that 3-SAT is as hard as SAT. So there is a reduction from SAT to 3-SAT. What's the meaning of that? It means that the 3-SAT is as hard as SAT. Then whenever you want to solve, I mean, instead of, you can always assume that the number of clauses in the problem is at most 3, because you know that this 3 version, how it is more restrictive, it seems, but it is not, and it is as hard as SAT. So it means that these 2 problems are equivalent, because SAT was each of these problems belongs to class NP. This means that these are equivalent. So the question, actually do this thing. This is some poll. How many of you have seen, I mean, how many of you have heard about the SAT problem before? Raise your hand if you have seen SAT problem. Okay, good. So it is like half of the class. That sounds good. And now, this is the question. Can somebody says that why SAT problem is why 3-SAT is as hard as SAT? Why we can reduce SAT to 3-SAT? Actually, while you're thinking, let me just add something, then we can go to this one. It is important. So there are some versions of SAT that we are talking about it. So one version of SAT is the 1-SAT. So if there is a 1-SAT, it means that in each clause there is 1 variable. So is the problem easy or hard, essentially, if it is 1-SAT? Any ideas how can we solve the 1-SAT problem?
It's easy. It should be easy.
Why?
Because you can check every single clause, and
so in some sense, as I mentioned, each clause either it has X or it has X bar, correct? For some variable that we have. So we have N variables, say, correct? So if we have this clause, it means that it is X or X bar. So if it is X, it means that X should be true. If it is X bar, it means that X should be false. So if you go through all clauses, actually you can set all of these variables, and if there is, so of course, if we have something like this, one clause is X, the other clause is X bar, then we cannot satisfy it, because here it means that X should be true. This is AND of this, guys. So it means that X should be true here, and X should be false here. So there is a contradiction. If there is no such things, then we can solve it. Otherwise, we cannot solve. Is it clear?
yes.
So this also, if we have 2 clauses, so now if we consider 2-SAT, if we have 2 things, like we have X, Y, essentially, X or Y, or it can be X and Y, it can be, maybe it is X bar Y. This 2-SAT problem also you can solve it in polynomial time, and we talk about it later. So we talk about the 2-SAT. So 2-SAT is also solvable is in P. But 3-SAT is the first one. 3-SAT is the first problem which is actually is NP complete, and this is of course the 3-SAT, 4-SAT, all of them are somehow equivalent. But now coming back to this question, this was the important one to answer. why 3 sat is harder than sat. So we need to say, to show that, we need to say that if we have, so what's the meaning of this? Is a good actually exercise. We want to say that why 3 sat is harder than sat. So it means that what is the input that is given to us? Please unmute and answer. So the input is in the form of sat, correct? So what is the form of sat that we can have? So it might be the case that this clause, I mean, so what's the difference between sat and 3 sat? In sat, in 3 sat, every clause should have exactly 3 literals. In 3 sat, we don't have such, in sat, we don't have such a restriction. So in particular, it might be the case that one clause has only one variable x. So one easy way is if we can do that, if we can change, and this is we have and of these clauses. So if we can make sure that each clause that has no restriction on the number of literals, we can always somehow turn this input into a set of clauses such that each of them have exactly, each of them has exactly 3 variables in it, 3 literals in it, then we should be in a good shape. Good. So if we have one clause, it has only variable x. How can we make it into a clause of size 3? If we can do for every clause, so the goal is that for every clause we want to, if the size is not 3, we want to put some input, some equivalent clauses such that all of these clauses have 3 literals. So one case is that x, essentially there is one clause which has only x. What can we do in this case?
Add dummy variables.
How can you say more
Like
precisely?
just come up with new variables,
Okay.
and which are not used anywhere. So we could
Yes.
just
So
always
say
take them to be 1.
A and B. Okay, so we don't have this one. So this is the things that in the sat we don't have any way to put a variable 1. Because the input, I mean, we don't have any extra things that we can put a variable 1. We can only have these clauses and clauses of literals. That's it. So how can we make sure that, so he wants to put essentially A and B, both of them are equal to 1. If it is the case, so if it is 1 or true and this is 1, then it is, of course, then this one, actually you don't want to put them 1, you want to put 0. Correct? If these two guys are 0, because this is the or of these guys, correct? So we have x or A or B. So if we can put A and B 0, it means that the value dependent only on x. So that would be equivalent of this guy. Is it clear so far to everyone? So please unmute and answer. Is it clear?
Yes.
But the issue is that, I mean, still we have not resolved the issue. How can we force A and B are 0?
We can add more clauses.
What type of clauses?
Like X, how can you say that?
Yeah, you can A bar or A hat.
Yeah, A bar and B and then X, A,
yes,
then
good.
B bar.
So you say that, I mean, essentially we don't put, so we will just put these ones, X, A, B, that's one clause. This is all of these clauses. That one is not enough. So we cannot force, but if we can force it essentially like this. This is A hat and then B. x or of a, so then we have it now a and b bar or b hat, and then x a bar and
Yeah, every combination.
so every combination. So if you put every combination, it means that at least in one of, so this we cannot force that a and b become 0. But when you put this one, we can make sure that at least in one of these combinations, both of the first guy and the second guy, both of them are 0. Any way that you will put it. In that one, of course, those that are, one of them is 1, then we are satisfied. No worries. But there is one of them that both of them are 0. So in that case, x should be always what? X should be always 1. That's exactly the meaning of the clause. So that's the case that if x has size, the clause has size y. What about if the clauses that the size are 2? What can we do for them? So please unmute and answer. So if a clause has size 2, how can we turn into a clause of size 3 essentially? How can we change? You note that here we have changed this input from this x, we change it to this one, and then we give the procedure that solves the problem. Essentially, that solves the 3 set. But what about if the input has 2 variables? What can we do in this case?
It seems like we can add another variable.
Yeah.
Do something similar, like.
Yeah, exactly. So we can do the similar thing. So we can have x, y, and then say a here, and then say x, y, and a bar here.
Yeah.
Good. So again, a and a bar, one of them would be false. It means that in that case, it forces x and x or y should be correct. So that's the thing that we could solve it. So these are the variables of length 1, the clauses of 1 literals, clauses of 2 literals. And of course, if the clauses of 3 literals, we are already there. We don't need to do anything. Now, the only problem is that for the clauses that their size is greater than 3. What about if we have a clause of size 4? How can we do that? So note that this is exactly the type of, so lots of this class, the assumptions are the one that, of course, you will just, learn in this class, and something that you can memorize or they are in the books, etc. So that's the easy part, essentially. The intelligence parts are this reduction parts are the algorithm. So in some sense here, we need to change the input of one function to the input of another function. And this is by itself and is an algorithm that it needs to do that. There's another function that is coming and change the input. So this is exactly the reductions that we are talking here, and possibly the output. For example, here, the output would be easy. In this case, if we get any results here, we should ignore A and B. So we don't, these temporary variables that we have added, just ignore the values of them and report the values of the original variables. That would be the output. So whenever this is, as I mentioned, so we are going from A to B. So we change the input from A to B, and then we need to, this is the change the input of A to input of B, and then we need to also change the output of B essentially to the output of A. That's the thing that we always need to do that. But yeah, so now let me. So say if we have this variable, so we have X, And again, I will just mention x, but x can be actually a negative. This is the literals that we are considering it. X, y, z, w. So, and again, each of them is a literal. Y can be y bar. There is no, but this is without loss of generality. We can do that. So the issue that this has a class of 4 variables or 4 literals. How can we turn it into a class of 3 literals?
Can we just split the 4 variables into 2 sets of 2?
Yeah, okay. Then what do we do?
And maybe we can add some more variables like A and B to represent them in a way such that by adding more clauses, you can guarantee that A always equals X or Y, and B always equals Z or W, so that they can be represented
So
as.
in some sense, I mean, the idea that you are talking about it, this is maybe we can do it X, Y here, then ZW here.
Yeah.
But then what can we do after that?
And you can like add 2 more variables, A and B.
Okay, yeah, A and B, yeah.
And in order to guarantee that X or Y always equals A, maybe we can use 2 clauses here. So one is X or Y or A.
Okay, Y or A, yeah.
I just realized that you need one more and here. So
Okay.
I have to think about how to do that.
So
yeah, we
yeah.
always have the ands of ors. Yeah, go ahead.
Yeah, so yeah, it seems like we can add C. Okay, the first clause is it seems good. Then C A bar, then B,
Yeah.
and then the W and another.
It becomes too complicated.
I think if you want to do it with just A, you could have like A represents whether there's a truth value in Z or W. So then you just need one more clause, which is like not A or Z or W.
Okay, so repeat then. We have what are these clauses that we have?
So that same first clause, and the second clause is
So you mean X, Y, and A, X and X or Y or A, and then what?
Z or W or not A.
Good. So you want to say this one essentially. So you may do this one. I will do it here. So we have X, Y here. Then we will put it A here. And then here I will also add this A bicar. Correct?
Yes.
So here I have X, Y, and A, like X, Y, or A. And this one is A bar or Z or W. Correct?
Yes.
Now, good. So in that case, either A would be true or false. If A is true, then it means that, of course, this is true. So if A is true, then this is the whole thing is true. But then A bar would be false. So it means that one of Z and W should be true. And vice versa. So if A is false, so then in this case, then X and Y, one of them should be correct. So it means that independent of whether A is true or false, at least one of these X, Y, Z, W should be what? Should be true, correct? Everyone agrees with that?
Yes, yes.
Good. Now, okay, so so we could just add one variable, and independent of that, we could solve the issue. Now, what about if we have one more variables as well? So what about if we have it one more variables? You see, this Zoom actually has become better from previous year. They had this, because before they didn't have this arrays that you can do this one. So what about if we have, I don't know, Y, Z, what the other things we can put it? Say put it T here. So if we have, what about if we have size 5? What can we do in this case?
We can do the same and do something like divide and conquer until we get all the clauses have the 3 literals. Okay.
You want to do the same things until okay, so
Yeah, basically we can add 2 more variables.
oh, okay, so yeah, I mean, about the recursion, you need to be careful, because the recursion, you need to say that the value goes down, because if you add this, because in some sense in the recursion you are adding new variables. So for example, if you want to do it here, so you may do it essentially like this. So you will add it X, Y, I don't know, another variable maybe A here, and then you need to add A bar here. So in some sense, this guy, also the size of this guy went up essentially by 1. So you need to make sure that always this recursion actually ends in a correct thing. But this is a general idea. Yes, I mean, you can try to do this one, but here you are adding this A bar to this class. So in some sense, you are adding new variables, and you need to be careful to make sure that the sizes are going down and you can get it that one. But what was the other thing that is mentioned? So someone else mentioned some other ideas.
So can we do something like X or Y or A, and then Z or W or B, and then T or A bar or B bar? 3 clauses and 2 extra variables.
Yeah, I mean, you need to check all the possibilities. So this idea of recursion that mentioned, that is actually a reasonable thing. You can check that, you need to check that everything works, but there is actually a simpler formula. So what can we do here? And this is more general. So that works for 5 or more than 5. So what do we do? So we have here X, Y. Then for this one, I will just use, so here I will add it A. Good. Now, what about for the next guy? I will add it A bar. Then what do we do? Then I will put it Z here. And then I will put it B here. Then I have it, the next one, I have it B bar. W C here. And finally, the last one would be C bar. By the way, by comma, I mean essentially or. C bar, then actually you can put it T. Or I mean, if you want to do this one, maybe that is, we actually clear this one. Good. So let me just put good. So I will put this chain of variables A bar, B, and B bar, and you can continue this one if it is more than that. So if there are something, so these the first two guys have two variables, the last guys have two variables, everyone else has only one variable. Now it's actually easy to see that because of this thing that we will put it. So here this is like somehow similar to this idea that we discussed here essentially. So here either A or A bar should be correct in some sense. So if A is false essentially, then X and Y, one of them should be correct. But you can choose that actually A should be false, A should be true. It means that we don't care about X, Y. Then in this case, if A is true here, then A bar should be false here. So in this case, you can then either Z is true that is desired, or if Z is essentially false as well, then B should be true. But if B is true, then B bar should be false. So in that case, then one of the W and T should be correct. Is the idea clear? Sorry, please unmute and answer.
Yeah, it's clear.
Yeah. So you can actually check, I mean, yourself. That's a good exercise that we can create it. And this is if and only if. If there is an assignment for this variables of size 5, this is for this one also there's a true assignment that one of them is true and vice versa. If it is this one is true, also this should be true. So that's the exercise. But again, this is somehow, in some sense, this is this recursive idea that we discussed, but it is a in a very clean way. Great. So this is and exactly the thing. So now we solve this problem again. You can just when you want to change the output, you will just ignore the variables of these temporary variables, and then you will report for this one. So we will change the input, give the procedure that solves for 3 stat, and then from the output we will get the solution for the original stat. And that's always we are doing that. This was one example of the things that we are doing a lot in this class. That's essentially the main thing that we do in this class. And these are all of them are algorithms. These are just some gadgets or algorithm, you can say that. Great. So let me clear this one now. Okay, so this is for NP hard. So the 3-sat is very important problem. Now, what about for PSPACE? So 3-sat is an NP-complete problem that we are using it a lot. But for we are using constraint logic for the PSPACE completeness. So what is this problem? So the problem is this one. Given a directed graph, so there is given a directed graph with age weights 1 and 2. So the age weights are 1 and 2. Find a sequence of age reversal to reverse. So okay, so this is some directed graph is given to you. And we can assume actually all the degrees are 3. Good. Actually, this is yeah. So so this is the graph. So all the degrees of these vertices are 3. So at most 3 vertices are coming to each vertex. And the weights again 2, 1, 1, 2, and so on. Maybe, yeah. And maybe this guy to this. So it is not acyclic, it can have cycle. Good. So an original graph, given a directed graph with age weights 1 and 2, as we have seen it here, and a sequence of okay, so what is the so at any time you wanted to, what is the operation that you can do it in this graph? You can consider one edge and make it just reverse of that edge. So instead of this direction, you can make this direction. And what is the goal? Is that some edge is given to you like this edge. You want to start from anywhere and just make sure that you will reverse this edge essentially. So the goal is to reverse one particular target edge T. Okay, but what are the operations? So the edge reversal. So the issue is that why don't you just reverse this edge and you are done? So the goal is to reverse one particular edge. What are the operations? Is that at each time you can reverse the edge, essentially the weight of the direction of each edge. The problem is this one. Then why don't you go on the target edge, just reverse it, the one that is. The issue is that you need to have this, this is a very important property. The in weight at any time, the in weight of any vertex should be at least greater than or equal to 2. What's the meaning of that? So at any time, the weight of the degrees, so for example, for this guy, the weight of this guy is 2 because there are edge of 2 is coming. Here, there is the weight of incoming edge to this guy is only 1. So this is violated. So this should be not the original graph. So in the original graph, you should have this property that in weight means the weight of all things that are coming to this one should be at least 2 for all vertices. Now, you can start and change any edge that you want, as long as you don't violate this condition. The in weight of every vertex, the sum of the weights of the vertices of the edges that are incoming to a vertex should be at least 2. As long as you don't violate this, you can start changing the edges one by one. And the final goal is to change the change the direction of one particular target edge that I'm giving to you. Does it make sense? Is the problem clear? Or if there is a question, please ask me either way. So please unmute and answer. So is the problem clear? Then you say yes. If not, please ask question. Either way, any of you.
I have a question.
Yes.
So you say that the in weight has to be at least 2, but in this input graph, the in weight is not like at least 2 for at least one vertex.
Yes, I mean, yeah, this is not a valid input graph. Originally, some valid input graph is given to you as well. Good. I just created this as example. But you need to add, I mean, the input graph satisfies this property. This input graph that I have mentioned does not satisfy it. But the input graph that is given to you, it satisfies this property. And you need to keep this property all the time, and you can reverse the edges as long as you want.
Okay, sure.
Such that a target edge is reversed. So this problem is called Constraint Logic for PSPACE-complete. And this is a very powerful tool for proving hardness of games and puzzles, that they are PSPACE-complete. For example, there is this Rush Hour game. You can read that one in the book. And this is the paper that Dimen and Harn actually proved that this problem is PSPACE-complete. You can see the ideas in the book that how you can use this problem to prove the PSPACE-complete. But one important thing, actually, I want to say that, so one question is that why this problem actually is PSPACE. So this problem, I mentioned that this is a famous problem that is PSPACE-complete. The complete part is hard because you need to say that this problem is as hard as any other problem is PSPACE. But I want to see why this problem actually is why this is a PSPACE problem.
You can try all combinations of reversals, whether that works or not. You can do this in polynomial space.
Yeah. Okay, but this is this one. So this problem that you want to. So why we can solve this problem in PSPACE? That's a question, correct? So here actually this is so that's important. So we want to say why this problem actually, if we have polynomial space, we can solve it. This is the very important one that we mentioned before. That this is the problem. You're using this theorem that I mentioned. In this non-deterministic or parallelism does not help that much or does not change the story for PSPACE. So PSPACE and NP-space are the same, but because of this Savage's theorem. Now, to say that this problem I can solve it in polynomial time, then of course the issue is that you can. So in general, you can guess and then solve the problem. Correct? You can try all possible guesses and then solve the problem. That's actually interesting. But these guesses that you need to do, because PSPACE is equal to NP-space, you don't need to do all this. So these guesses, so you can just use this theorem and say that for a given guess, I can see whether it is a solution or not. Correct? Because this theorem already says PSPACE is equal to NP-space. So, and NP was exactly this one. A certificate, a solution is given to us, and we want to see whether this is a valid solution or not. So essentially, now this problem, if you want to see how you can solve it, it might be non-trivial. But if we use this PSPACE is equal to NP-space theorem, it says that if a solution is given to you, if essentially the order of the edges, the operations, the edge reversal are given to you, whether this is a valid solution or not, that would be very easy because we can just check it and just go through that, just do that whether it satisfies it. So PSPACE is equal to NP-space actually helps us a lot to say that this idea of that we can try all possibilities, that somehow will be hidden in this PSPACE to NP-space. I only need to check whether a solution, a solution that is and a certificate which is given to me as a potential solution is really a solution or not. I will, in the PSPACE, I can do all the changes because all the changes and then see, oh, whether this particular edge, that my target edge has been reversed or not. That's it. Good. So any question? So next time we are talking more about some other problem, which are other NP hard problems. So we talk about the 3-SAT and 3-partition. These are two important problems. For constraint logic, if we have some time, we will talk about it. Otherwise, you can read it from the book, from the examples that this from constraint logic. Actually, we can use it to show that several other problems and games, these are actually PSPACE-complete. Good. No more questions. I think we will finish the session here. Okay, bye for now.